Today I'm going to talk about how to make sparse code fast. And I'm going to focus on the Taco domain-specific language we have built for sparse tensor algebra. So if you look at out there, tensors are everywhere. From data analytics to machine learning to science and engineering, you can find tensors. For example, if you go look at data analytics, a lot of these tensors keep sparse data. So let me explain why sparse data is very important. So let's say look at the product reviews for Amazon. So in this Amazon product reviews, you have all the Amazon products that they have ever sold, all the customers who have ever bought a product, and all the words they have used to write a review. So if you keep this as a dense three-dimensional tensor, the entire Amazon data center probably might not have enough storage for that. But this is extremely sparse tensor. So if you just store the data that is has a non-zero value in this tensor, then the tensor can be stored in your probably laptop or desktop. So this shows you why it's extremely important to store these kind of tensors in the sparse format. However, today the state of art of getting sparse performance is using kernel libraries. But this doesn't scale very well. There are many tensor kernels written for linear algebra. There are kernels written for data analytics. And even things like quantum chronodynamics, there are very specialized tensor kernels in here. So there are many kernels that you won't operate on. Even let's look at a more simple kernel that every respectable tensor library supports, which is sparse matrix vector multiply. So one simple function. But there are many implementations of this function because you want small variations, and if you have a specialized function for that variation, you can get good performance. And in fact, OSCI alone has 282 versions of sparse matrix vector multiply. Why? There are different shapes and sizes of matrices that you might want to optimize. Also, when it comes to sparsity, there are many different representations. So for example, thermal simulation matrix can be represented using a compressed sparse row. If it is even more sparse, you can do doubly compressed sparse row. Sometimes there are dense blocks within the sparse format, and at that point you want a block sparse compressed sparse row format. And data analytics use things like a coordinate format, and there are many other formats for different type of applications. And there's a single dimension user vector, and more than two-dimensional matrices you have other formats. The formats are endless. And then of course it depends on where you want to run. You might have to write a different kernel. So if you look at this product of all these things, you suddenly realize writing all these kernels by hand will be a full-time occupation for a very large number of programmers. So we don't want to do that. So if you can't write every individual kernel, what do? One approach the dense community have taken is, why don't you write bunch of binary operations like multiplication, addition, here matrix multiplication, element-wise matrix multiplication, and then you combine them to build compound expressions. Yes, you might lose a little bit performance because of caches, but better than nothing. However, this is very different in sparse domain. So let me explain why using this simplified dense matrix multiplication or SDDML. So this kernel take two dense matrices, multiply them. So of course now if you are doing component, you can find a very fast implementation of that. And in here you want to get a 64 inner products, and then you do element-wise multiplication of that with a sparse matrix. So now if you want to calculate this value at location 4, 5, you have to get this inner product calculated and multiply by that value, you get it. That's great. But how about this value? You don't have to do any multiplication because multiply by 0. So now you calculated the 64 inner product to throw away 54, and only 10 inner products are used because B matrix is sparse. So if you do this component-wise separating, you're going to do a lot more extra work than necessary. In fact, you can be asymptotically slower. So just to give you a performance number, so if you do the separate operations, you can be thousands x slower than if you do this as a single compound operation. So this is why you need to generate specialized function for each and every expression when you have sparse operation, lot more than in the dense case. However, generating sparse code is complex, lot more complex than dense code. So let's look at these 3 tensor multiplied by a vector. If everything is dense, this is a code probably even a first year undergrad can write. However, when things became sparse, so this B now is a complex sparse fiber format, then the code gets a little bit more complicated. And when both B and C are sparse, if C is in a compressed format, the code gets even more complicated. And even if you have different sparse formats like a hash map, you need a completely different type of code to be written there. Again, complicated. And if you think this is hard enough, if you are adding 3 tensors from 2 different formats, to get the best performance, you have to write this piece of complicated code. So writing this by hand is no easy task. This is why we won't do it by the compiler. So we built this compiler called Taco, the tensor algebra compiler. It can take an expression, any tensor algebra expression. For the tensors, any format out there we can use. And then also we have a scheduling language like Halide that you can use to do further optimizations. And now we can produce code for C to run on multicore or on the GPU. And we're also working on some other backends for this one. And this is open source, so you can go and take a look. So let me now get into why this is not that simple. What are the challenges of sparse tensor algebra compilation? So the first challenge is the sparse data is very irregular, the data structures that is represented. So how to deal with these irregular data structures? Second, sparse iteration space put a lot of limitations for how you can iterate, how to deal with that. Third, as I showed you before, you want to avoid wasted work and how to do that in the most efficient way. Finally, you might want to do some optimizations to get good locality and parallelism. So let's go into each of these possible. So the way we address the irregular data structures, that every different representation has a different data structure, is to come up with a standard way of simplifying it called hierarchical storage abstraction. So before going to that, let me explain a little bit of how these sparse representations are and what they look like. So we have this 2D sparse matrix, and normally in memory these are in linear order, memory order. So if you represent it in the normal dense way, this is your representation. It's a very nice representation, and if you want to get to some location, we'll say 1, 2, you basically calculate 1, 2 by looking at the access function, and you can immediately go and access that location. That's very easy. But there's a problem here. There's a lot of wasted space here. All these empty spaces still has a memory location, and I showed before, this can be extremely expensive. So instead of doing that, you want to represent only the non-zero values. So you keep it here. Now how do we find a row and a column? There's no other data. I don't know where it is. So I need to keep some extra data. So one way to do that is keep both row and column coordinates. So now it's very easy to find 1, 2. You look at the row 1 and you find the column 2 in there, and then you suddenly know the index of the data. However, one thing people realize is in here, there's a lot of redundant data in the row representation. So you can basically eliminate these duplicates in a format called compressed sparse row format. So there, what you can do is you have a very compressed representation. Now from that, I can find my values. So now if you get to a 3 tensor, so like compressed sparse fiber has all these different data structures representing the indices out of there. So normally all these different formats used to have different data structures. Each seem to be different. But we came up with this observation that we can come up with a much more simpler way to represent this. So if you look at these things, each dimension has a couple of data structures, so we can separate that. So the outer dimension here is dense, so you only need to know how many elements are in this dimension. You don't need anything else. The next dimension seem to be using this compressed representation, and the final dimension, column dimension, just basically has one value for each basically row. So we can say the first representation, the dense format, the second is this level compressed format, and the third is what you call a singleton format. There's only one value for each incoming value from the previous level. So using these three level representation, we get this. So these were three representations. So assume we go back to our two-dimensional matrix in here. So if you put a dense outermost and a compressed innermost representation out of our three possible representations, this is a CSR format. If you use a compressed outermost and a singleton innermost representation, you end up with a coordinate format. So in fact, using these three level representations, we got these two. Many other formats out there can be represented using these three formats. And in fact, some other things like block CSR and LPAC type formats can be represented using by adding additional dimensions of using these level dimensions, and we can actually get that. And in fact, if we add few more level formats, we can more or less get all the formats people have described today in this representation. So now what we have done is, instead of each representation being something very different, hard to figure out, we came up with 6 level representations, and we can use those 6 again and again to represent all the different sparse representations that's there. So the next interesting thing is sparse iteration space limits how you can iterate over that. So let me give you an example in here. And the way we solve this is using what we call sparse iteration graphs. So here's a sparse representation. You have all three dimensions are compressed, and they are interconnected together. So now I don't have order one random access. I can't just go to, we'll say, locate 202 anywhere I want, any location. In order to go 202, first I have to go first dimension and locate 2, and from that locate 0, from that locate 2 again, and then and only then I can find the value in here. So I can only go I, j, k direction. Any other direction you have to iterate a lot more, they are going to be a lot more expensive. So let me show you, this is a 3 tensor multiplied by a vector. If 3 tensor is dense, I can represent it using this dense 3-dimensional iteration space in here. These are the values in here. And this k is 1 dimension, but we can of course replicate in the other 2 dimensions and get that. And so you're not iterating over these two separately, you're iterating them together, you're co-iterating. So you overlap those iteration space and you do the multiplication. This is how we calculate a dense value in here. However, if B and C are sparse, we have some additional restrictions. So B, I can only iterate I, j, k in that order. And C, I can only iterate k, that's only 1 dimension. And then I have to merge these two and co-iterate. And interestingly, because I am doing a multiplication, I have to intersect all these values and only iterate where things are intersecting. And then I have output that I am producing in the ij dimension. This gives me the sparse iteration graph. The nice thing is, for any tensor algebra expression, we can write a sparse iteration graph by looking at the format. And what I'm going to show you next is, if you have a sparse iteration graph, generating code for that expression is very mechanical. So here we go back to our original expression, assume output is dense. The B is a dense compressed representation, and C is a compressed representation. These are each level in here. So we generate level by level. I is a dense, there's only B coming in, so it's very easy to generate that. And J is also compressed, but it's only 1 coming in, so you generate iterating over B if it's a compressed dimension in here. And then for C, you have 2 things coming in, B and C. Now you have to co-iterate over that. And you generate the co-iteration code, and finally inside we do the compute statement in the innermost place. So now I went by level generated code. So you might be wondering, how did I get this co-iteration code? So the next complexity is how to do that. Again, as I showed you before in the original example, if you are co-iterating over multiple things, if you do it wrong, you can do a lot of extra unnecessary computation. So you need to figure out a way not to do that. And the way we did that is what we call using co-iteration code generation. So to do co-iteration code generation, we use a data structure called a merge lattice. Let me explain that using a very simple element-wise vector multiplication. So if you do element-wise vector multiplication of two sparse vectors, only output happens if there's a value for both B and C. So that means you need to find the intersection. And I use this as a lattice. So there's an intersection in there. If either B is not there or C is not there, you are done. If B finishes or C finishes, you are done. There's no value in it. So then you have an empty set. So B and C, I can generate code. What it says is I iterate while both B and C have values in here. And then I only have to generate output if both B and C have the same value. So when IB equals I and IC equals I, that means both B and C has that value I. Then and only then I generate AI in here. And then when you are done, nothing to do because there's no more values. If either B or C runs out of values at the end, we are done. This is very simple. This gets a little bit more complicated if we're actually doing addition. So here what I'm going to do is add BI plus CI. And let's figure out how to do this one. So addition requires union. So I represent union, but I want to simplify it a little bit. Union can be divided into three parts. One is when both B and C have values. And then the other two parts is only B has value or only C has value. So I can create a lattice like this in here. So the top element says both B and C have values, and then only B has value or only C has value. And then if both runs out, then you're done. So now I can mechanically generate code here. So assume both B and C have value. So I go here and I iterate until B and C both have value, and if either one runs out, I am done with this loop. And now we have to generate in a loop in here. So the first thing is, if the I is in both B and C, that means in the intersection in there. At that point, I actually do the addition. But I am not done in here because this is a union. Assume there's no value in C, but there's a value in the B. I just have to copy that value out. Same thing for C. So if both are there, I do the addition, otherwise I just copy. Now assume I run out of C and only B is left. So now I can just copy the rest of the B into the output. Same way, if I run out of B, I copy all C's, and now I got the entire union in a very efficient way executed. So when things get more complicated, you don't have to worry. You have this very mechanical way of getting a merge lattice and generating code. So what happens is you go through each of these lattice points and look at what's there and keep generating code for the lattice point. And this looks complicated, but it can be done completely mechanically, generating this code. We can even do a little bit more optimization. Now here we assume both B, C and D are sparse. Assume now D is dense. What does that mean? What that means is, if D runs out, you cannot have any B or C. So you can never end up in a situation you have only B and C. You always have to have D. So then when you look at this lattice, bunch of these lattice points disappear. Because you always have to have a D. If D runs out, you are done. So what that means is I can generate code that is a lot more compact in here because my lattice is now much more smaller. And so I can even optimize like that. So what this shows is I generate the minimal amount of code. I am not doing any extra computation when I know if a value is not there. So this is how we do avoid doing extra work. So we can actually show that by doing this, we will never ever compute some value that will later get multiplied by a zero. So this is how we avoid doing wasted work. So by doing these merge lattices, we guarantee that you will never calculate a value that will later get multiplied by a zero and disappear. So that extra value is never be done. So in that case, we are asymptotically better. Or we will never perform a computation where addition, where one side of the addition is a zero. That computation will never happen. We'll just copy the data. So by doing that, we eliminate all these asymptotic slowdowns we'll get otherwise if we just do the same thing we do for dense computation. The next thing I want to talk to you about is optimizing for parallelism and locality. So if you look at sparse computation, it is again a computation that has bunch of loop nests iterating a bunch of array. But given these are not simple loop nests and not simple array accesses, they are much more complicated. But again, this has the similar notion of dense computation. And there are a lot of optimizations we do for dense computation to get better locality and good parallelism. So what we did in this case to get this optimization is to come up with a scheduling language. We came up with a scheduling language with a scheduling API that's very similar to the halide language. So if you know halide, you will know that we can use these commands to things like the split the iteration dimensions, reorder the iteration dimensions, and parallelize, unroll, and do these computations and get really good performance on modern microprocessors, CPUs, and also GPUs. So we can do the same for sparsely, but there are a little bit more complexities than dense. So let's look at one of those. So if you want to split the iteration space, in the dense case, what we do is we look at the iteration space you want to look at, the coordinates, and you can split the coordinates into equal size. Assume I want to split twice, so I can split the coordinates by half. This works perfectly if they are dense, but in the sparse, there's a small issue in here. If I just do this, what you realize is the first half has most of the work, and second half has very little work in here. So this is not a really good split. So we can do better splits. So now what you want to do is now the outer iteration has 0, 1, 2, and 5. So not instead of dividing at 2, you want to actually put 2 iterations on one side and 2 iterations on the other. By doing that, you get a little bit of better load balance programming. So this is what we call the position space splitting. Because you are splitting the space, not the coordinates, but the data actually here. Again, if you look close, this is not exactly load balance because the inner dimensions have different number of iterations. So if you want to get a really, really good split, you actually have to split the inner dimension. So if you look at the inner dimension in here, the iteration space gets split in a very interesting fashion. But now we have a much better load balance program at your hand. So this is the kind of things you want to do, and these are the additional things we have to do if you want to get good performance on sparse iteration space. Now, let me go and show some results out of that, what you can do. Here's the code for sparse matrix vector multiply, where A is in a CSR format and the vector is dense and the output is also dense. So this is a normal code that we will generate. But now we can start using our scheduling language to control that. So first thing we do is go and fuse the ij dimension and get a new dimension. And then now you can do is convert that dimension, the fused dimension, the innermost dimension to position space. Now you get all the contiguous things that are allocated into one dimension, And then I can do it, I can go and split that dimension into multiple times. Here we split it 3 times, and then we did the reordering to get equal size blocks. So now I have 3-dimensional blocks which are all equal size by doing this splitting. And as you see, I have named these things thread, block, warp, and thread. So as you guess, I'm trying to go and generate code for a GPU. And now I can go and figure out what of these loops, how to parallelize this. So we can say what gets assigned to blocks, what can assign to warps, and what gets assigned to threads. And we generate this code automatically, both the node code and also that codes go in the GPU all get generated automatically with the right communication. Now we might not be done yet. Now after you do GPU, we can even do additional optimization. For example, here we do some pre-computation, initialize and set up some computation locally in local memory so that I can do things faster. And then I can do things like unroll certain loops and get better performance. So you can do a lot more optimizations and get better and better performance in here. And next what I'm going to do is show you some results. So this is the code generated for GPUs. First one is sparse matrix vector multiply, and we are comparing against handwritten code done by NVIDIA, their best engineers handwritten code. And what we are showing here is our automatically generated code using the handwritten schedule, which is much more easier to write than writing the entire code, get pretty good performance, very close to what NVIDIA engineers were able to generate. And for the MTTKRP loop in here, again, we are getting the best possible performance for all the programs compared to all the other hand implemented systems out there. So in general, if you look at it, we can generate code for any of these expressions. However, it's hard to compare. So what we did was we generated code for expressions people have written hand optimized code. So here are 3 of them. So sparse matrix vector multiply is an extremely popular piece of code. Many people have written code for this and hand optimized for this. And the best possible performance, low is better here because this is normalized execution time. The best parallel implementation you can find is in Intel MKL, and we are getting performance either match or exceed the Intel MKL performance in here. And STDMM code, as I showed you before, our code matches the eigen library, which actually also hand implemented this function, and uBLAST, where you try to do component-wise calls, it's much worse. Yeah. Same thing here for MTTKRP. The Splat library has hand implemented this kernel, and then we are matching our generated code. Whereas Tensor blocks is trying to use component operations to get that, and it's much worse. So next, let me explain how you can use Taco. We have 3 flavors. First is a C++ library. There you can go define your tensors, what formats they are, initialize the tensors, either reading from a file or basically copying data into it, and then do the computation using operator overloading. And when it's a compile, it will in fact dynamically compile this piece of code using LLVM, link it into this, your binary, and then you can assemble the tensors and compute it. And we also have a Python binding for this, so you can do that. Finally, we have this online code generator where you can go in there, write your own expression, give the formats in there, and it will generate the code. So what we find is many data scientists who has some computation they want to perform, instead of using the library or something like PyTaco, they will go here, write the exact expression you want to do, generate the code, and then basically cut and paste that. The nice thing about that is this has the least number of dependencies to your code base, because what you have done is you have one very exact code in C++ that you cut and paste in here and use that. And we are finding that this is the most popular way of using Taco today. So thank you for listening to my talk. I have listed some other projects that we are working on in my group. We are dealing with a lot of DSLs and also using machine learning inside the compiler and also generating fast machine learning code using compiler techniques. And if you're interested in Tahoe, here's the URL. You can find the papers and the code at this location.